talk about waves, electrical energy, and sound energy. We're going to review what we did in class with the different labs that we did and get ready for the upcoming quiz. So in our first slide, if we look at waves, and sound travels in waves, and sound, like we said, is a measure of the vibration of things. We showed how we pluck a guitar string and it vibrates, and it vibrates to the air to our ears. And we watched a video of Steven Tyler's vocal cords, and as they vibrated, it created these waves, these vibration waves that went to our ears. So let's look at waves. From the midline to the top here is called the amplitude. And the amplitude can be the height, or it can be the depth down here to what is the crest at the top or the trough at the bottom. And that's the amplitude. The bigger that amplitude, think of the word amplify, the louder it gets. So if I have a really big amplitude, it's a really loud. A really small amplitude, it's small. If you remember from playing with the oscilloscope app that we had in class, it showed that. From crest to crest is a wavelength. It doesn't have to be crest to crest though. It can be from any 2 points that are the same. Like this is the beginning of it going up the hill from the midline. So from here to here would also be a wavelength. From the bottom of a trough to the next trough would be a wavelength. From say right here to right here would be a wavelength. A wavelength is a measure of um, the distance from any two identical points on that wave. We usually say crest to crest because those are easy to measure, but it could be trough to trough or from midline to midline at the start of the wave, either way. The closer those waves are together, let's take a look at this. The closer those waves are together, the faster it's moving, and that means it's got a higher pitch. When we looked at the oscilloscope app, the high pitch frequencies, they have really fast moving, really close together waves. The lower pitch frequencies, the waves are farther apart, have much longer wavelengths. So we can tell by looking at waves, both the volume, the amplitude tells us how loud, and the frequency tells us the pitch, or how high or how low. If we look here, we have a chart of how fast sound travels through different types of medium. And if you look at the solids, we have granite and we have steel. It travels much, much faster through those than, say, a liquid. And a liquid travels much, much faster than, say, through a gas. A sound has to have molecules to vibrate, to travel. The closer those are together, the faster it will travel. So granite and steel go much, much faster than, say, oil and water. And oil and water go much, much faster than, say, oxygen and nitrogen. If you wonder, it says oxygen travels and nitrogen both much slower because their molecules are much farther apart. Solids, they're real close. We did a little activity in class where you're tapping on the desk and you could see how fast sound could travel. If we go to the next slide, we're going to look at electrical energy now. Electrical energy is about the flow of electrons. And remember, don't ever play with electricity at home. When we did it in class, we did it with things that had high volts but very, very low amps. Volts is the pressure in which those electrons are pushed through, but the amps is how many electrons. It's the difference between, I showed you, like a water gun and a fire hose. If I shot you with a water gun with a certain pressure, it wouldn't hurt you. But say a whole river went with that same pressure, it knocks down houses and cars. And so a lot of amps is what causes damage. And we did not play with anything that had a lot of amps. We did things with a lot of volts, so it was kind of cool when we saw the sparks, but we didn't do anything that was dangerous. So never play with electricity at home. Types of circuits. Circuit comes from the same root that circle comes from. It means to go around. It always going to start at the negative end, and it's got to go all the way around to the positive end to complete the circuit. If at any moment that circle is not completed, everything gets cut off. It's got to go in a complete circle. This is called a series circuit over here, and it goes through all the way through. And this is a parallel circuit. And the way I remember parallel, it starts with a P, and it's got more than one path. So in this circuit, in a series, if either of these light bulbs go out, they both go out because it stops the flow. It's like a traffic jam, and the electrons can't keep traveling through. But in a parallel circuit, if one of them goes out, well, they just go a different path, and the other one still stays lit. So the lights in our classroom, I showed you, were done in parallel because one was burnt out and all the rest were still lit up. So those electrons had another path to go through. So this is series, and this is parallel because there's more than one path. Last thing I'm going to say is that electricity travels well through something called conductors. Metals are great conductors of electricity. The electrons can flow from atom to atom in metals really well. Things that do not conduct electricity well are called insulators. And you see here on the wire, they have a rubber insulator. That's so you can touch the wire and you can do things and move that around without getting shocked because the electrons will not flow through the wire. If you remember in class, I shocked aluminum foil, and you can see the spark fly to that, the electrical current fly to the foil. But then I tried to do it to a balloon, and nothing happened. So balloons are good insulators, metals are good conductors. Conductors allow electrons to flow. I hope this helps, and we have our quiz on Monday, and I will make more of these as we go through different topics. Thanks.